Hey everyone, welcome to this Explainer Masterclass. Today, we're going to unpack analytical learning specifically for your Module 5 exam. We are stepping away from those massive data-heavy datasets and looking at how AI can actually learn from pure logic. So if you're preparing for your V2 machine learning examination, you're in the exact right place. We're going to tackle this from a foundational, conceptual understanding level straight through to the specific keywords you absolutely need to score maximum exam marks.
Okay, let's take a quick look at our roadmap for today. We'll start with inductive versus analytical learning, then look at the safe-to-stack example, define perfect domain theories, break down the prologue EBG algorithm, explore the capabilities of EBL, and wrap up with its limitations and inductive bias.
All right, let's kick things off with Section 1, Inductive versus Analytical Learning.
So, if you get a 5-mark question asking you to define analytical learning, this right here is the absolute crucial distinction you need to make. While inductive learning relies solely on training data to find a hypothesis, analytical learning goes a step further. It gives the learner a domain theory. Now, what is that? It's basically background knowledge used to explain the observed examples. Think of it kind of like this. Inductive learning is like trying to figure out the rules of chess just by watching thousands of random games. It takes a while, right? Analytical learning, on the other hand, is like watching just one single game, but you've got a grandmaster sitting right next to you explaining exactly why a move was good based on the fundamental rules of the game. That prior background knowledge, that's your domain theory.
Moving right along to Section 2, let's look at the safe-to-stack example.
Let's ground all this theory in a real, highly testable scenario. First, we have to define our instance space. We use predicates, things like volume and density, and we define our target concept, which in this case is safe-to-stack. We're looking at a hypothesis space that's entirely made up of horn-clause rules. And what's cool is that the system can use basic mathematical functions, plus, minus, and times, along with logical predicates like less than. The ultimate goal is simple. Find a hypothesis from this space that perfectly aligns with both our training data and our background knowledge.
Imagine we feed the system a positive training example. We tell it, hey, it is indeed safe to stack this red cardboard box on top of that blue wooden end table. Now, if we were using purely inductive learning, the system might actually get a bit confused here. It might start guessing, oh, maybe it's safe to stack because the box is red, or maybe it's safe because a guy named Fred owns it. It just doesn't know which attributes actually matter because it completely lacks context.
Well, here is where the magic happens. We introduce domain theory B. These are prior knowledge rules. Think of rules like, it's safe to stack if the bottom object isn't fragile. This allows our system to logically reason way beyond just surface-level observations like colors or shapes. For instance, the domain theory might state an object is fragile if it's made of glass, or an object is lighter if its weight is less than the other object. Notice how predicates like lighter and fragile weren't even mentioned in our original training example. The system is literally using its background knowledge to deduce much deeper logical truths.
Let's dive into Section 3, Perfect Domain Theories.
Now, for this logic to work flawlessly, we need a very specific, somewhat idealized type of background knowledge. Listen up, because this is a classic 6-mark or even 8-mark VQ question. A perfect domain theory absolutely must be two things, correct and complete. Correct means every single rule we provide is a genuinely true statement about the world. Complete means those rules are comprehensive enough to explain every single possible positive example in your entire instance space. If you have this perfect setup, you unlock the true power of explanation-based generalization.
Which brings us to Section 4, the prologue EBG algorithm breakdown.
You absolutely need to master this core algorithm for an 8 or 10-mark question. At its heart, explanation-based generalization uses a sequential covering approach, and it relies on 3 core steps. First, explain. It literally proves the example satisfies the target concept. Second, analyze. It looks for the sufficient conditions that made it true. And third, refine. It formulates a brand new general rule. The system learns a single horn-clause rule, removes the positive training examples that are covered by that new rule, and then iterates on whatever positive examples are left over. It just keeps repeating this until all positive examples are fully covered.
If you only remember one thing about this workflow for your exam, make sure it's this. Prologue EBG uses domain knowledge to derive logically justified general rules. It's not just hunting for statistical patterns. It stops only when absolutely no positive examples remain uncovered. The flow is fascinating. It starts by creating an explanation, a mathematical proof really, that the example meets the target concept. Then, it analyzes that proof to find the most general set of features that are sufficient to satisfy it. And finally, it refines its set of learned rules by plugging in this newly discovered general condition. This is where it all clicks. The system literally builds an explanation tree where it deductively proves that safe to stack is true simply because object 1 is lighter than object 2. In doing so, it entirely filters out all the irrelevant fluff. It uses its domain theory to calculate weight based on things like volume and density, proves 1 is lighter, and therefore proves it's safe to stack. It completely, 100% ignores the fact that the box was red or that Fred owned it. Why? Because those facts were totally useful for the logical proof.
And this highlights exactly why analytical learning is so incredibly powerful. It determines which example attributes are actually relevant by regressing the target concept. That's a great keyword to use, by the way. It regresses the target concept to formulate a justified general hypothesis. It doesn't guess, it proves. Each newly learned horn clause becomes a sufficient condition for satisfying the target concept, which means the system can instantly handle any future instances that happen to share that same logical explanation.
All right, moving on to Section 5, Capabilities of Explanation-Based Learning.
Let's synthesize what makes EBL so effective in practice. This is another highly testable area. Memorize these key phrases. EBL performs knowledge compilation and example-guided reformulation. What that actually means is, it takes a big, clunky, complex domain theory and transforms it into lightning-fast operational rules using just a handful of examples. Instead of doing the heavy logical reasoning from scratch every single time, it compiles that knowledge into efficient rules that can classify new instances in just a single step. And honestly, the most mind-blowing part? Because it relies entirely on strict logic rather than statistics, EBL can successfully learn a highly effective general rule from just a single positive example. One example, that's it.
Finally, let's cover Section 6, Limitations and Inductive Bias. Now, examiners love to ask for the weaknesses right alongside the strengths. So a major limitation you definitely want to write down is that EBL is entirely 100% dependent on human experts defining an accurate domain theory. If the rules those experts write are wrong, or if they miss something, the system's conclusions will be completely wrong too. And building that domain theory? It requires intense expert knowledge engineering, which is incredibly difficult and time-consuming. Plus, a lot of critics point out that EBL doesn't technically discover net new knowledge. It really just mathematically reorganizes the knowledge the human expert already spoon-fed it.
Mathematically, this limitation is super interesting. It's formalized by a strict deductive constraint. It basically shows that the hypothesis, which we call H, must logically follow from both the data D and the domain theory B. In pure inductive learning, H just has to predict the training data. But here, the constraint is rigorous. D and B entails H. This massively reduces the ambiguity the learner faces simply because the domain theory heavily restricts which hypotheses are even mathematically possible to consider. So what's the ultimate takeaway about Prolog EBG's inductive bias? Remember, inductive bias is just the policy by which a system generalizes beyond its training data. Well, for Prolog EBG, its bias is simply the input domain theory itself, plus a slight preference for small sets of maximally general horn clauses. Because the hypothesis follows deductively from the domain theory, the algorithm's entire worldview, its entire bias, is completely inherited from whatever background knowledge we, the humans, fed into it.
Which leaves us with a pretty provocative thought to ponder as you wrap up your studying. If analytical learning depends entirely on the absolute perfection of a domain theory, how do we build resilient AI when human experts, the ones writing the theories, constantly make mistakes? It's a huge challenge in the field. Keep that in mind as you review your notes. Best of luck on your VTU Module 5 exams. You're going to do great, and keep leaning into the logic.